Hello. Today I want to talk you through a sample Bayesian network that I've created in JavaScript. Well, in fact, as it turned out, very little JavaScript was actually needed. On the other hand, the HTML took ages, and you'll see why in a minute. Here's the setup we shall be considering. It follows the exploits of an irresponsible motorist whose actions lead to punishment from the courts, and is subdivided into 6 statements. Firstly, the person might or might not have consumed alcohol before getting behind the wheel of the car. Secondly, the vehicle itself might or might not be defective. You know, broken rear light, tyres as bald as Yul Brynner, that sort of thing. Now, either of those 2 things, or a combination of them, might lead to the motorist being involved in an accident, or being arrested by the police. It's quite possible that the police, investigating the accident, arrest the motorist anyway, particularly if he fails a breath test. Finally, after the wheels of justice have turned, 2 possible penalties are listed: compulsory attendance on some sort of rehabilitation course, or the revoking of one's license to drive. I have labelled each statement with a letter, which is how they are referred to in the JavaScript, and included arrows to suggest cause and effect. Both the consumption of alcohol and or a defective vehicle can cause an accident, and both or either of them can lead to an arrest, as can the accident itself. Of course, it is perfectly possible to be arrested for some vehicle-based offence without either being drunk or having had an accident, and the probabilities will take that into account. The arrow in the centre of the screen indicates that, while it is perfectly possible for involvement in an accident to lead to an arrest, the reverse is most unlikely, as one tends not to have a road accident after one is taken into custody. The screen for the network is crowded with tables of data, too many for me to include them all in this explanation. Here are the first 2, which give the probabilities of the motorist having consumed alcohol and the probability that his vehicle is defective. Each is based around 2 input fields, one for the positive statement, i.e. the probability that the vehicle is defective, and one for the negative opposite to the statement, i.e. the probability that it isn't. I have listed the HTML code for the 2 fields for statement A. A similar one exists for B. Note the name of the field and the call to function neg. The names are specified carefully so they reflect the probability that they represent. All field names start with P and an underscore, followed by what they're the probability of, and then the letters GIV, followed by the items on the right of the given that symbol. To indicate not in a probability, the line above the letters in the hieroglyphics, it's indicated by preceding the letter with a lowercase n. An example on the next screen will make this clearer, but right now we only have 4 fields called P_A, P_NA, P_B, and P_NB. The positive and negative pairs of probabilities must add up to 1, or rather 100%, as everything is specified on screen in terms of percentages. After all, if the probability that your car is damaged is 20%, as suggested here, then the probability that it isn't must be 80%. The whole idea of these input fields is that you can alter the probabilities and then recalculate to see how the resulting figure changes. However, we must maintain this add to 100% relationship between fields, and that's where the function neg comes in. Neg is called when a field loses the focus, the on blur in that code. This might be because you want to alter another field's value, or because you want to click on the calculate button. It causes the value in the other one of whichever positive-negative pair of probabilities you happen to be in to adjust so that they add to 100% again. More on this in a later slide. Here's such a pair of fields from a table lower down the page. The probability for D, road traffic accident, depends on both A and B, although the first entry in the table, P of D given not A and not B, indicates that it's perfectly possible to be involved in an accident with a car in perfect working order and not having touched a drop. Note the name for the highlighted cell on the left, a P followed by a D, and then GIV, followed by an A, and then NB, all separated by underscores, indicating that this is the probability of D, given that A has happened and that B hasn't. The two biggest probability tables are for E and F at the bottom of the screen, which depends on the states of A, B, C, and D. This means that each of these tables has 16 rows in it. I've chosen one as a sample, and you can easily map the combination of A, B, C, and D into the names of the two fields. The order of the items in the name is important, so that the JavaScript can access it. At the bottom of the screen are 8 radio buttons, in two groups of 4. Use these to specify which probability you want the network to calculate. The way the system is set up, you can calculate the probability of either of the two original causes, drinking or defective vehicle, given the final outcome, rehabilitation course or license revoked. The default checked option is to calculate the probability of A given E, the probability that alcohol was consumed given that the motorist ended up on a rehabilitation course. The first set of buttons sets the part of the probability required before the given that symbol by calling the function get. The second set determines the part of the probability after the given that symbol by calling the function given. Under those is the button do it, which calculates the probability and displays the result in a span called result underneath that. Now for the JavaScript, and as I say, there isn't much of it. The first line is an array of two elements, index 0 and index 1, which is used to place a letter n in front of any of the letters used. We will be using nested for loops to go through the different possibilities, and this array will be used to construct field names from those for loop variables. The next two lines set up the default values for the variables get what, which will be A, not A, B, or not B, and given what, which will be E, not E, F, or not F. The default probability calculated will be the P of A given E. You can see this from the definitions of the two functions get and given here, which simply set these global variables to the parameters provided. And now we have the definition of that famous function neg. The field that has just lost the focus is the first parameter, field name, and the one which has to have its value adjusted as a result is the second parameter, opposite name. The function itself simply reads the new value in field name, doesn't even check to see if it's a number, and then writes 100 minus the value into the opposite name field. Beneath the function definition, I have included example calls, this time for the table for statement C. The first input field calls the function with the parameter corresponding to the name of the input field itself. Compare the two. And the second parameter, the field to adjust, is exactly the same except with n in front of the letter C, i.e. the field sitting to the right of this one on the screen. This second field, opposite name, has exactly the same parameters in its call to neg, except the other way round. This time it is the field with the extra n in its name that has just lost the focus, and the field to be adjusted as a result is the field to its left on the screen. This way the two fields on each line act as a linked pair. All the probabilities that we will need will be of this form, i.e. the probability of either E or F, and A, B, C and D, with any combination of those letters made negative with the not symbol. We can't read those probabilities directly, but by splitting them up into chains, as shown, we end up with values that can be read from tables. That's why I've written C and D in that combined probability before the A and B, to show how the sequence naturally breaks up into the tables that we have on the screen. We have made one assumption at the end, namely that A and B are independent, i.e. whether your car is shonky doesn't depend on whether you've had a drink or not, and vice versa. We can find the probability of A and B both happening simply by multiplying the probability of A by the probability of B, which of course we already have. Here's the JavaScript for that equation. Each of the field names that we need is constructed as a separate name, and then the value is read from the appropriate field. Strictly speaking, values read from the field are strings rather than numbers. But the first thing that happens is that we divide them by 100 to turn them from percentages back to decimal fractions. And that has to convert them from strings to numbers in order to work. The function has 5 parameters. The first one is the value of given what, i.e. E, not E, F or not F. The other parameters, A to D, are either blank strings, assuming we want the positive probability, or the letter N, if we want the not version of the probability. And here's the function that does the calculation itself. What you see at the top of the screen is a very simple version of Bayes' rule. Let's suppose we want the probability of A given E. We have a fraction where the numerator is the probability that both A and E happen, and the denominator is the probability that E happens regardless of whether A happens or not. Function calculate works both these out. There are 4 nested for loops, one for each of the value of A, one for B, one for C, and one for D. Each goes from value 0, representing the positive probability, to 1, the negative or not version of the probability. So between them, these loops cover all combinations of these statements from all false to all true. The chain probability for the particular value of E or F that we want is calculated for every combination and added to the variable prob given what. This corresponds to P of E in the example we're using. If the combination that we have calculated also happens to match the condition for A and B that we specify, then it is also added to the variable prob of both, which is the numerator of this fraction, corresponding to the probability of both A and E in our example. All that remains is to calculate the probability required by dividing numerator by denominator, and to display the result to 3 decimal places in the HTML span provided. And that's it. All rather anticlimactic, really. If you want, you can check the program is producing correct results by crashing through the maths on a calculator or spreadsheet, but it's a real pain in the neck. Try changing the probabilities to see how the calculated result changes. You should be able to work out which values in that table are the most important to change if you're trying to affect the result that pops up. I can't think of many ways you could improve this sample program. I suppose you could add a feature where you could calculate the probability of any of those 6 statements given the state of another one. For instance, the probability of not C given not F. Alternatively, how about adding further statements at the end of the diagram, G and H? I'm not sure how you would add to the scenario about dangerous driving, though it could be done, I dare say. Perhaps you would need to come up with a totally new scenario that would fit the expanded network better. You can probably see already why that last idea is a non-starter. With only 6 statements in the network, we already have tables of 16 entries in them. If you add more levels, tables at the end of them will at least double in length, possibly even more. That's the thing about Bayesian networks. The amount of data that you need explodes exponentially with the number of nodes in the network. That's probably a good place to end this video. As always, if you liked what you have just seen, please click on the like button below and consider subscribing if you haven't already done so. It would also be remiss of me not to point out that I have both a Subscribestar account and a PayPal link listed in the description below for anyone who might want to support my work financially. Thank you.